Thank you. The schedule said 20 past. Never mind. Does that mean I get more time or less time? Right. Let's put this away. Okay, plug in. Make sure I'm on the right slide. How you doing today? You good? I brought the weather with me. I normally bring rain. Everywhere I go, it rains, but today, last 2 days has been amazing. So this is fantastic. I'm a little bit worried that spring, we kind of missed spring. We've gone straight to summer. And I like spring. I like spring a lot. Oh, there we go. All right, let's make sure my clicker works. Dump my phone. Make sure my phone doesn't go off. Nobody phones me anymore. I don't do phone calls anymore. I keep telling people I don't do phone calls, and they keep phoning me. But. Right, okay. Hello, everyone. How you doing? Container scheduling, a practical guide. So I'm going to be talking mostly about Kubernetes. I'm not going to be talking about Docker Swarm and things like that. I think I should do, actually. I'm kind of worried about what the timing is now because I have no idea when we're going to finish. So let me run through this very quickly. This is me. You can get me on @TechGirl on Twitter. And how many of you are using Google Plus still? Everyone laughs when I say that. No, I still use it. It's still really good. It's got more than 140 characters, which is pretty cool. So you can also find my Twitter handle on every single slide, right at the bottom there, and along with the GOTO Stockholm. And support the event. The event is fantastic. It's really amazing. They're doing these events everywhere in Europe. And let's talk about Kubernetes. Get straight in there. I used to talk about Borg, our cluster scheduler, the thing that we have in Google, and compare Borg and Kubernetes together. I'm not going to do that today. There are talks of me doing that online. And there's also a guy called John Wilkes. He talks about Borg. He's one of the guys who builds our infrastructure. And Borg is the thing that ultimately takes all of the work that our software engineers do and runs it on our clusters, our large data centers. And Kubernetes is kind of an attempt to make that kind of power available to everybody. Not just at Google scale, but a very small scale. 10 machines, 5 machines. You don't need to have Google scale to do this. Kubernetes ultimately is a strange word. How many of you can say Kubernetes? If you need lessons, I'll be outside. I will be able to teach you how to pronounce Kubernetes. Kubernetes. It's a kind of Japanese word, and I'm using Japanese as well. But it's really Greek. It means helmsman. I'm not going to get into that. But ultimately, its goal is to run and manage containers. And that's good, because we ultimately probably have a lot of containers by now. Because you've probably all discovered containers. How many of you haven't discovered containers yet? Yeah, nobody put their hand up. That's good, see? You end up with lots of containers, and you need something ultimately to manage them for you. And that's what Kubernetes does. And I mentioned Borg earlier, the thing that we have internally, and Kubernetes is ultimately informed and inspired by Borg, that thing that we have internally, and all of the experience that we have building that thing for the last 12 years or so. It does support multiple clouds. It runs on AWS just as well as it does on Google Cloud Platform. So there's no lock-in here. There's nothing to do with Google. This is a community project, which is why I don't have the Google logo anywhere. Maybe on the first slide, I'm not sure. It supports bare metal environments as well, so you can run this on-prem, you can run it on AWS, you can run it on Google Cloud, you can run it on DigitalOcean, wherever you want to. It also supports multiple container runtimes for some value of multiple. We have a couple at the moment. We have Rocket and Docker. And now we have an open container format, effectively. We probably have more container formats that we can run, ultimately, on Kubernetes. 100% open source, and is written in Go. Go is extremely popular for this type of application. And ultimately, the goal is to manage applications and not have to worry about machines. Even if you're operations, you shouldn't have to worry about machines too much. Most people nowadays, when I ask a question about whether you're developers or operations, people say, a little bit of both. Right? So everything at Google runs in containers. All the things that you use, all the services you interact with on Google run in containers effectively. The container was a byproduct of what we needed to do. And ultimately, we worked with Linux to create C groups and namespaces, which is the thing that powers, ultimately, Docker and other container formats. We run our map reducers and our batch jobs in containers, and even our Google Cloud Platform virtual machines effectively run in containers. So if you run a container on Google Cloud Platform virtual machine, you run a container on a VM on a container. We launch over 2 billion containers per week, but let's not think too much about what a container is. Let's not worry about it too much. It's a process. It's a process that carries all of its dependencies around it and has a tool chain and has an ecosystem. But ultimately, when you spin up a container, you spin up a process. And you can do more than one process, but ultimately you care about one thing in a container. So if you think about 2 billion processes as being, 2 billion containers being 2 billion processes, then it's not such a big stretch to get to 2 billion. So you discover this, ultimately, you've done all this work. This is replaced all my containers slides. I used to have an explanation of what containers were, 10, 12 slides, and I'll replace it with this one slide, which is containers are awesome, so let's run lots of them. And that's a natural conclusion for most people to reach when it comes to developing applications today. Containers are good, we want to run them. But where do we run them? How do we run them? How do we manage them? How do we do their updates? How do we wire them together? And that's the kind of thing that Kubernetes ultimately deals with. With Kubernetes, you start with a cluster. The cluster could be a laptop, so you could run using the Vagrant provider. You could spin Kubernetes up on your laptop using, ultimately, VirtualBox as your virtual machine provider. I think it supports VMware as well, probably. I've never tried that. You can also use multi-node, high availability clusters, on-prem or in the cloud. They can be hosted or self-managed. We have a managed version of Kubernetes. But you could be managing it yourself. It could be on-premise. It could be on the cloud. You could run on bare metal or virtual machines. We support pretty much every operating system, even... sorry, I forgot what it's called. Exactly, I forgot what it's called. So you lose your word, right? So we actually implemented it on top of this Raspberry Pi cluster, and that's a 5-node cluster running Kubernetes. You probably don't want to run that in production, though. And ultimately, if you want to find out more about how to fit it to your needs, there's a cluster, there's a matrix, a cluster matrix there at the bottom, a link, and you'll have the slides at the end. Setting up a cluster is fairly straightforward. I meant to update this. We don't use this kind of bash script, pull down a bash script and run it immediately after pulling it down anymore. Nobody does that anymore. So that's a bit of a legacy. So you'll pull down the tarball, untar it, and then ultimately run the installer, setting your Kubernetes provider to something like GCE or AWS or Vagrant or CoreOS, depending on what you're running it on. If we don't have an out-of-the-box way of installing it on your platform, there's plenty of recipes, and that goes back to the matrix on the other page. There are various distros, Red Hat Atomic, CoreOS Tectonic, Mirantis, Murano, and various others. And yeah, so there's recipes, and you can also use a hosted version such as Google Container Engine. And this is what Kubernetes looks like, ultimately. We have a bunch of machines, nodes. We used to call them minions. Again, calling things slaves and minions is a little bit not so nice. So now they're called nodes. And each node in the cluster runs this thing called a kubelet. And the kubelet has the credentials it needs to be able to connect to the cluster and become a member of the cluster. And so when these machines come up, they find the master. We have a single master. They connect to the master via the API, and they become part of the cluster. And the scheduler, which is also part of the master, the slide probably needs a little bit of an update, and that's wrong. I'm not going to change that. We use etcd for configuration management, but it's Raft-based, not Paxos-based. So that's a mistake on the slides. That's kind of what Borg does. Then we also have dashboards and we have controllers. We also have a container registry as well. So because we care about running containers, things like Docker or Rocket, then we care about where those images are located. And this container registry could be hub.docker.com. It could be some registry you created for yourself, because it's fairly easy to set them up. Or it could be also on Google Cloud Platform if you're using Google Container Engine. And ultimately what happens is we push an image out to the container registry. We provide a configuration, push that out to the K8's master. The scheduler comes along and looks at the state of the system, what it is currently, looks at the state of what it should be, as according to our persistent storage, and it says, okay, there's different, let me fix that. And so it will make the actual state the same as the desired state. So we have this notion of desired state. And then the scheduler, whoops, the line's gone round the back, the scheduler will decide where that work will run, those resources will run, and it will talk to one of the machines, and the machine will pull over the binary, or the image, and then run that container on that machine. And the scheduler's work is what we're going to be talking about today. And somehow that line's got stuck at the back there. So that's basically how Kubernetes works. But let's go into some of the resources that Kubernetes provides. So the first is the atom of scheduling. We don't use containers directly to schedule work on Kubernetes. We use a thing called a pod. And a pod can ultimately run multiple containers. It's a bit of a convenience, but if you think of it like a logical host, if you create a machine and you run multiple processes on that machine because they need to work together, they have some kind of synergy, then it makes sense to have them in a pod. So effectively what you're going to do is take that machine, which could be virtual or logical, and you're going to take it into a format and convert it into a pod that can run on a cluster. And just like a machine, it also has its own IP address. So we can be running multiple of these pods on a node, but each of them will have its own IP address, which is not natted. So we can talk to it directly via its IP. And all of the containers running inside the pod have a shared namespace. So the idea of the port namespace is the same for multiple containers running inside the pod. And they can talk to each other via ports, or they can talk to each other via IPCs, because they have a shared IP namespace, IPC namespace as well. So containers running in a pod look like and think that they are running on a single machine. So effectively, we're creating these machines and we're scheduling them on our cluster. That's really cool and really powerful. And we also have volumes, the notion of volumes. This example shows two containers. One of them is a very simple Node.js application serving traffic externally. There's other mechanisms we can use to expose that externally, which we'll see shortly. And we also have a Git synchronizer. And its job in the world is to synchronize with a Git repo. So whenever you push changes to your Git repo, the Git synchronizer will see the changes, pull them down, store them on the volume, and we can now serve those updates to users. So it's a kind of push to deploy mechanism. But again, they're just two examples of containers. This is what we call a sidecar pattern, where there's a synergy between the containers. There are also other patterns as well. Often you may only run one container in a pod, which is perfectly fine. There's no overhead. And we said that pods can talk to each other via IP addresses directly. That's the way it works. We have an underlying overlay network. For Google Cloud Platform, that's our advanced routing. For AWS, it's route tables. We can use Calico or Flannel or Weave or Open vSwitch or Cloud Provider or Open Contrail and others. There's also one from Cisco Contrive. There's probably some I've missed, and if anybody's representing those companies, I do apologize. But yeah, so it's fairly easy to set up. But again, if we have multiple pods on a node and they're all exposing the same port, that is fine. They have their own port namespace, effectively. So if you have multiple pods exposing port 8080 on the same node, that's fine. That will work. These are fundamental requirements. We have to have this for Kubernetes to work. We also have the notion of labels. Labels is the single grouping mechanism of Kubernetes. We can label pretty much everything in Kubernetes. And then we can build tools to read those labels. A label is a key value pair. It doesn't have any semantic meanings to Kubernetes, but it probably has semantic meaning to you. Like the role equals something, the type equals something, the color equals something. Something that has semantic meaning to you that will allow you to group these artifacts, these resources within Kubernetes. Here we see them applied to pods. We have pods with multiple labels. Resources can have multiple labels, and we're building dashboards and tools that will use those labels. And the way we use labels is via a thing called a selector. And so basically, we just say to the API, give me everything or all of the pods with this label. And we provide with this label based on the selector. And we have services within Kubernetes that also use that mechanism to group pods and to group other things as well. The service is the way we get access to these pods that are running containers. They expose a port ultimately. There's no NATing, as we mentioned. But ultimately, we have 3 identical pods all running the same Node.js application, Nginx application, but they're all identical. Then we need to somehow route traffic across them. We need to communicate with it anyway, even if there's only one pod. And to do that, we put a service in front of it. So the service construct effectively groups a number of pods from 1 to many. And the service provides a stable virtual IP address and also a DNS entry. So clients can access those running pods via that virtual endpoint that we provide in there. And traffic coming in from the clients will be load balanced across multiple pods. And it's done randomly currently. It used to be round robin. So that's the service. This can be used to discover services internally. So we could be wiring things together internally. Or it also could ultimately expose an endpoint externally as well. So we have the notion of a load balanced endpoint. And if we have a cloud provider, such as Google Cloud Platform or AWS, we can actually expose the service on an external endpoint to the rest of the world. So you have multiple different types of services. We also had the notion of replication controllers, which are now being superseded pretty much by replica sets. They are the same. We're just trying to get away from, well, they're mostly the same. We're trying to get away from using controllers in the names of these things. Because everything started to be a controller, and it kind of got confusing. So now we've decided to confuse everybody by changing their name. So now they're called replica sets. But they are fundamentally the same as replication controllers. So if you're familiar with them, then you won't see much change. They do have a new generalized label semantics. So rather than just having equality for labels, you can have inequality, and you can also do sets. So like a value in some set of values. So we can do labels a little bit differently with replica sets. But fundamentally, they're the same. And a replica set ultimately is responsible for making sure we have our desired state for a given pod deployment. We provide a pod template, which contains the containers, ports, labels, and such like for creating pods. We say how many we want. In this case, we want 2. Well, 1, 2 in the left-hand one and 1 in the right-hand one. And we pass that in as a configuration to Kubernetes and say, make it so, effectively. So we say, we want X number, and we want this template. The replication controller will wake up and look to see if there are any pods that match those labels that it has. In this case, it cares about label version equals v1. And so it will look to see if these exist. If they don't, it will make an API call and ask the API to create them for it. And it will continuously monitor to make sure there's always the right number running. Okay, so if you've asked for 2, there'll always be 2 running. And it's fairly straightforward. We can have multiple replica sets, many, many different replica sets managing different pods. But they may even be just different versions of your pod. We've got some scenarios coming up. We'll show you. Deployments are very new. We have the ability to do a rolling update to those pods. So once we updated our image, our container image, we may want to roll that out as an update, a rolling update to our service, our production service. And the way we used to do that was a thing called a rolling update. And it would basically create a new replication controller in those days, which would create one new pod, take an old pod away, create another new pod, take an old pod away, and eventually it gets to a state where all of the pods have been replaced, and it can remove the old replication controller. But that was all done on the client side. So you could do Control-C at any point, and you would be left in an unknown state. You could finish it off at some point later, but it was fairly unpredictable and liable to problems. So the deployment object is something new that's introduced in 1.1, which is now in beta in 1.2, but it's also the default, as we trust it so much. And this effectively does our rolling updates for us on the server side. So we basically create the deployment. I'll demo it shortly. We create the deployment, we push it out. It will create the replica sets for us. And if we want to update, we can just edit that configuration using the command line. Very, very simple. It's very powerful. And then it will roll out the updates to the pods. And you don't have to worry about it anymore. It's not happening on the client side. So that's deployments. Scaling is fairly straightforward. We can just change the number. We can instruct the replication controller or the replica set to have more pods. In this case, we say want you to have 2, it will create another one, or it will ask for another to be created. If we say we want 4, it will go ahead and instruct the API to create another 2. And it will then continuously check to make sure there's always 4. So scaling is very, very straightforward. And at the bottom here, we have a service, which cares about labels with type equals FE, and all of the traffic coming in to this service will be routed across, load balanced across all of those pods. Okay? Rolling updates are done like this now. So we have this deployment object. We have a replication controller. Again, it's managing 2 pods. We have a service down here, which I haven't put the name in. So these 2 pods here are being managed by this controller, and this deployment is managing this whole thing. And when we update the deployment, maybe by changing the image, what will happen is that we will create a new replica set, and we will then create tell it to scale to 1, scale the old one down, and then scale the new one up to the new number of pods. So ultimately, we've done a rolling update now. So we've updated all of our pods to the new image. And we're left with this spare replica set here. This doesn't go away. Because basically we create these replica sets based on a hash of the template that we use for creating pods. So we hash that template, gives us a number, and we add that to the name of the replica set. In this case, all we've done is scale it down to 0, and if we ever reuse that template, the same template, we can reuse that replica set. But at the moment, it just sits there with 0 pods. A canary is very simple. So sometimes you want to roll out an update to a partial update, just to test it, to do A/B testing effectively. In this case, we have 2 replication controllers. We have one with version equals v1 pods, and one with 1 version equals v2 pod. And the service is aggregating all 3 of those and load balancing traffic across all 3. So 33% of our traffic will go to this pod, and 66% will go to these 2 pods. And so we're effectively canarying. We may have 1 pod out of 10 to do an even smaller percentage. But ultimately, we can see the results come back for that new version. If we like it, we can then roll out a deployment update to update it completely, or we can roll it back. So that's how we do canaries. And we also do auto-scaling, which I'm not going to really cover. Auto-scaling is based on performance metrics, utilization, and we can scale clusters based on that. So that's very scale pods based on that. That's very easy. Jobs, we also have the ability to run short-running jobs, batch jobs effectively. So these will run to completion, and there's various rules that you can set for them. So pods no longer had to be long-running. There were ways to make them not long-running before, but now we have an official job. So you can effectively say, I want to run this to completion. You push it out to Kubernetes, it will run and finish. And that will be it. And we also have liveness and readiness checks. People ask about how we know whether the pods, the running pods, are live. Well, we have the ability to set up liveness and readiness checks, both at the process level and also at the app level. But I'm not going to go into details with them. But you'll see the slides later, so you can get access to this. And also the ability to gracefully terminate pods. If we're doing downscale events, we're scaling downwards, we need to be able to shut down the pod gracefully. So we give it a 30-second window of opportunity by sending it a signal. So then the pod can do its own cleanup. In the future, we'll hopefully be able to do some kind of draining. We'll be able to make lame ducks that can be taken out of the actual pod management system from the replication controller's point of view, and we can take traffic, stop traffic from going to it. So it can finish processing its requests, and once it's done, we can remove it. We don't have that currently, but we probably need it in the future. And also, we support multi-zone clusters now. So if you have, on Google Cloud Platform and on AWS, you have the notion of zones, availability zones in AWS. Now you can have parts of your cluster across multiple zones. So if, for example, San Francisco or the Bay Area was to fall into the Pacific Ocean for some reason, and you lose a zone, you'll still be good because Europe will still be up and running. We don't want that to happen, by the way, so I'm going there next week, or this week even, so let's not have that happen. So that's really good for availability, and that's available in GA now in Kubernetes 1.2. And just going to run through scheduling very quickly. I wanted to do my demo. Anybody know how long I've got? You have about 10 minutes. 10 minutes, okay. All right, I'm just going to go through the scheduler. Okay, so scheduling, basically, when we schedule things, we send some object to the API server, and this scheduler will look for new objects that have been stored in the configuration, and it will schedule them. It will make a decision, ultimately. It will decide where it's going to go. It's going to decide which node. The arrow should have appeared afterwards, but it will then schedule it on a node that matches its scheduling policies. The scheduling policies can be controlled, and we'll go into them shortly. But it has to make that decision on which node. Without a scheduler, nothing can happen, really. So we can send something to Kubernetes, and it won't know what to do with it, because it has no scheduler. But you could do it manually. You could say, I want to run it on this specific node. And you provide the node name when you send it. Say, basically, run this pod, or run this service, or run this pod, effectively, on this node. That's the old way of doing it. And that's the mechanical way of doing it, where you have to identify a machine. If you have a large data center, it may be a machine in a rack, a single machine in a rack, in a cluster, and decide which one you want to run it on. And that's not very good. So that's why we have a scheduler. We have the scheduler make all of those decisions for us. Kubernetes understands resources in terms of CPU and in terms of memory. And we can request given levels of CPU and memory for our pods. So we can ask for 2 CPU cores, or 2.5 CPU cores, and 10 gigabytes of RAM for a pod, because we know that's what it's going to use. And Kubernetes can then basically schedule based on the resource availability on those nodes, because you have a certain amount of cores available in your cluster. You have a certain amount of memory available in your cluster. And Kubernetes can therefore make a decision as to where this can go, because it will fit on there. Because it needs 2 cores. Where does it go? Where do I have 2 cores available? And also, we can also set limits, so that if you go above your limit, we can then say, I'm sorry, you've run out, you're using too much memory, we can kick you off. That's how we handle memory, because memory can't be compressed. We cannot throttle memory allocation. We can throttle CPU allocation. We can use CPU quotas in the Linux kernel to say, we're going to control how much CPU you have access using quotas. But for memory, we can't do that. So CPU is compressible. It can be throttled, but memory can't be. So if you use too much CPU, you'll just be throttled. You won't be able to use too much CPU. You've asked for so much, you're only going to get so much. If you ask for too much memory, you'll be kicked off, because you're trying to do something that we can't allow. You may compromise other running processes. Yep. And ultimately, a request and a limit are 2 things we have. We can specify when we're asking for memory and CPU for a running pod. A request is basically how much you think you're going to need for this, and it may be based on empirical evidence. It probably will be based on empirical evidence. This is what you think you're going to need to be able to run this. Right? So it's effectively the minimum you need. And if you say you want this much resource, we will only run it on a place where there's that much resource available. Okay? So if we need 2 cores, we'll run it on a machine that has 2 cores available. We won't overcommit that. So if you have lots of pods requesting 2 CPU cores, and you have 8 CPU cores, you can run 4 of them on it. But you can't run any more. We will never overcommit a request. So we're effectively guaranteeing that you have that amount available to you. But you also have the notion of a limit, and the limit is the maximum amount of a resource you can request. And for a pod to be scheduled, ultimately, all we care about is that the amount of requests is available on a single node. But if you ever hit the limit, then ultimately we're going to kick you off, or we're going to throttle you. If you request 0, then we can always schedule your pod. But you may not get anything. You may not actually be able to do anything, because you'll have no CPU shares. But if you request 0 and you go into a node that's empty, it'll run. It'll do whatever it wants to. It'll have as much as it needs. But it will be compressed down to the point where it may have nothing, ultimately, and it won't have any resources available to it at all. And again, we can't do that for memory, but we can do it for CPU. And ultimately, we can use different combinations of request and limit to set resource guarantees, or almost like protection. How much protection does a running pod have? So this is for CPU and memory. It effectively gives us quality of service. If we specify the request equals 0, then we're just saying, run me whenever you can. Run this pod whenever you can. If everything is maxed out, the whole cluster is maxed out, then it won't be able to run. It was scheduled, but it won't be able to run because it has no CPU shares. But if there's spare capacity, then it will be able to run and use whatever it needs. If you say the request is less than the limit, then you're saying sometimes, well, I know we need this much, but sometimes we need to burst and have more. And this is the limit we're going to go to. And that's basically burstable. We can run that. We can't always guarantee it's going to have that available to it. So if it tries to use more, it may be throttled or it may even be kicked off. For guaranteed, we specify the request and the limit to be exactly the same. So this is really the highest priority. It's not really priority currently, but it's basically the protection guarantee. So effectively, you're saying this pod will always be able to run because it's never going to want more than its limit. And when you specify your configuration, it looks something like this. You just specify the memory and the CPU for a request, and the memory and CPU for a limit on a pod. Actually, I should mention this is applied on a container level, not on a pod level. So if you have multiple containers, you can set different quality of service parameters for each container. And also, pod scheduling, we may care about other things as well. We may care about a particular machine has a particular thing that we need. It may have a graphics card, a GPU that we can use. It may have fast SSD disk as opposed to other spindle-based disk. So there may be something about a machine that means we want to run it there. So this is kind of like affinity, and we can do that with labels, and we'll talk about that in a second. But we may want a certain amount of resource, and we may also need certain disk. We may have created a disk that we need specifically, or we may just need a certain amount of disk that can be provided to us. So ultimately, with CPU and memory, when we're trying to schedule, when the scheduler is looking how to schedule this pod, it's going to look at the memory and CPU requirements, and it's going to find a machine or multiple machines that can actually have that resource available to it. Or if it's using a specific disk. An example, if I was able to do the demo, which I don't think I'm going to get a chance to, we have a MySQL pod, and the MySQL pod mounts a disk, and the disk has all of its data on it. It's effectively an InnoDB file system. And if that pod needs that disk, then we have to schedule it on a place where that disk is available. Now, the disk may not be mounted at all, in which case we can schedule it on any node, and we could then mount that disk on that node. And that's what Kubernetes will do automatically for us. It will schedule it on node, and it will find the disk and mount the disk for us. If it's already mounted that disk, then it will run it on that node because it needs that disk. And the same with, we have a thing called persistent volumes. So if you need a certain amount of RAM, a certain amount of disk, we would have created these things called persistent volumes, which you can mount in on demand. And also, you may, as I mentioned, you may want to run it on a machine with fast SSD disk or with a GPU or with some other configuration you need. And it may also be that you have some kind of affinity need. Maybe you have all of your machines in the cloud and some on-premise, which would be possible soon with a thing called Kubernetes. And that way you could actually say, I want to run it on these clusters, some on-prem, some in cloud. You'll be able to use scheduling mechanisms for node affinity to say only run on machines on-premise, never run this in the cloud. We'll also have this thing called anti-affinity coming up as well. So if you want to make sure it never runs on this, or never runs on a machine with another pod that might come into conflict with, or various other reasons why you may not want to run two things on the same node. And you can use anti-affinity policies to make sure that never happens. Okay, and that's coming up probably in 1.3. But won't be GA in 1.3, but it will be available. And ultimately, what we have to do is rank all of the potential nodes and decide which one to use. And then we have different policies. We can decide on whether to balance the CPU and memory, or make sure we have the machine, we leave the machine with the most free resources, or even make sure that the pods that we have are scheduled on different machines as much as possible. So if we have 10 pods and 10 machines, we should have one on each node. We have a bunch of things coming soon. You'll see this in the slides when you get them. Velocity, we're moving very rapidly up to 1.2. We're at 12,000 stars now or something. And 5,000 commits. We're now at plus 50% unique contributors from what we were with 1.1. So Kubernetes is dramatically, rapidly growing in popularity. And also, it's in the top 0.01% of all projects on GitHub, which is extremely significant, right? So 2 orders of magnitude less than 1%, or more than 1%. And so it's extremely popular. 800 plus unique contributors. We have many projects that are based on Kubernetes as well. Many companies contributing. It's not just Google. Red Hat are serious contributors to this, as are many of these others. And also many companies are already using Kubernetes in production. And in terms of plans, we're at 1.2 currently. 1.3 is in progress, should be in June. We're trying to do a 3-month release cadence. And we also have Container Engine, which is Google's hosted platform. It's the only time I'm going to mention Google stuff. There's platforms as a service, Red Hat OpenShift, Deis, Stratus. There's also distros such as CoreOS Tectonic, Mirantis Murano, Red Hat Atomic, Mesos. And finally, it's open source, completely open source. We are not governing this project. The community is governing this project. I used to work at Sun, and we did this thing called Open Solaris, and it wasn't really very open source at all. Kubernetes is fully open source, and it is easy for you to contribute. You can do pull requests, you can get involved in issues, and there's many really good debates on there. So if you're interested in helping Kubernetes develop, or you have a feature you need, you should go there and raise that question and talk to the engineers that are building it. Kubernetes.io is for the documentation. On GitHub, it's Kubernetes/Kubernetes. On Slack, slack.k8s.io. And on Twitter, it's @Kubernetes.io. The slides for this talk, my canonical deck is available there. So it has more than these slides. So if you look there, you'll see all of the slides for this talk and more. And that's it, basically. I've got time for questions, or?
So, we have a bunch of questions, actually.
Okay, cool.
We have a couple relating to region awareness. So, is scheduling for region awareness available? How do you do that? Do you use labels like you would for graphic cards, or is that a separate feature?
I think at the moment you'd have to use labels. There are annotations, so we can make sure that persistent volumes and nodes run in the same place. So we can actually identify where they're running through these annotations. We didn't talk about annotations, but they're kind of like metadata that can be attached to running objects, just like notes, basically. So we can use annotations effectively, but I think at the moment you'll probably have to use labels.
Okay. What about, so another question here about anti-affinity. You mentioned that it's an upcoming feature, but is there any way to deal with this today, if you're clever?
Is there any way? Yeah, so you could probably do it with labels. I mean, providing if you labels are not the best way, because you're really kind of limiting the scheduler to what your options are when it comes to where it can schedule its pods. And that's a bit of a problem. You're taking some of the power of it away from it. So you could say, only schedule these pods on these nodes, only schedule these pods on these nodes. And so if it's a problem of having maybe multi-tenancy problem, that could be a problem. We also have namespacing, but we can't schedule based on namespacing currently. So probably the best way is, again, use labels. So group things by labels, and that will probably work for you.
Okay. So do you see any benefit of running Kubernetes on top of Mesos?
Yeah, I think it's a good standards-based API. So I think ultimately, we're not really in the business of building clusters. So if there are other cluster mechanisms, then that's great. I mean, so if you can build a cluster somewhere and then stick Kubernetes on top of it, like you can do with the DCOS from Mesosphere, then that's fine. So any kind of cluster mechanism, anything that can actually run that stuff, provided we can stick a Kubernetes layer on top of it, then that's fine. Then all we have to do is rely on the cluster to do the scheduling, or to carry out the instructions of the scheduler for us. That's all we need to do. So yeah, so I think it's very possible. I don't see any, did you say any benefits?
Yeah, benefits.
Yeah, I don't think there's any benefits specifically.
Well, you could
But
have,
if you have familiarity with Mesos and running Mesos clusters, then that's great.
or if you have Mesos in your organization already and you want to use Kubernetes as well.
Exactly. If you're already using Mesos, you can stick Kubernetes as a shim on top of it, effectively. And then you can just move around as you need to. Portability is a great, one of the goals of Kubernetes. So I think that's having that API available, but not having to worry too much about the infrastructure underneath is really important. In fact, I mentioned Borg earlier. I'd love to see a day when we have, at the moment, we schedule stuff on virtual machines. We could effectively get rid of the virtual machines and just schedule them on Borg directly in the future at some point. So that's exactly the same thing. We have a cluster. We have a Kubernetes interface, a facade almost. And we send instructions to Kubernetes like we always would do, but we don't care about the mechanics of what happens underneath the hood.
Okay. So another question here. Will console be supported at some point?
I don't know. Will console be supported? I think you'd have to ask them. You'd have to go onto GitHub and find out. I'm not sure there's any plans, but I think pretty much everything that can be done with Kubernetes has been discussed on the GitHub project because everybody's interested and everybody's excited and everybody has their own problems they want to solve with it. So I think if somebody wants to run console, they probably would have raised it. It may be it went into a dead end. Maybe you could revive it. And again, I think that's the great thing about it is that you can just, this is what I want. How can we build this? And people will be interested and they'll tell you why you can't or why you can or how you can. So I think getting involved in those discussions is really important.
What about something like auto scaling? We saw that you could scale up by manually going in and say, I want 2 nodes. But could you write, is there any sort of support for that in Kubernetes already?
Yeah.
Or would you have to write an external program that would scale it up and down for you?
All right, so I would have talked about pod auto scaling. It's quite 30 minutes is quite short for a talk. So showing all of these things in a demo is hard. And auto-scaling demos are really, really terrible because auto-scaling is something that happens over a long period of time, not over in a 2-minute demo. So it never really works properly. But the fact is if you have one pod servicing traffic and you're monitoring the resource utilization of that pod, you can scale when it reaches a certain level and add more pods. And those pods will be distributed across the nodes and the traffic will be load balanced via that service to each of those pods. At some point, you may run out of nodes. You may not be able to schedule any more pods. That's the whole point of Kubernetes. You could potentially run out of nodes. And at that point, if you're in the cloud, we could auto-scale your nodes for some providers. So for Google Container Engine and Google Compute Engine, if you're on those, we can do it today. And we're looking for other people to do other mechanisms that will allow them to scale dynamically. But we can then scale more nodes and add new pods onto those new nodes. The one thing we can't do currently is rebalance. So once we've added nodes, we can't move things so we can flatten out the cluster again. That would probably come in the future where we can reshape the cluster based on adding new nodes.
Would you be able to schedule or scale based on other metrics rather than just load, like the face of the moon or
Absolutely,
the weather?
So I think so. Anything that could be measured, anything that could be measured on a scale and be scaled proportionally, then I think that will be possible. At the moment, we can do that with nodes already, so we can do that on lots of different metrics. So we can be monitoring the nodes and scale based on metrics that are happening on the nodes. So it could be disk utilization or something like that. But we really want Kubernetes to be the one that's responsible for asking the underlying runtime to scale, not having the runtime scale automatically on its own, because that kind of screws the scheduler up a little bit. So basically, we should have an interface from Kubernetes onto the underlying runtime so that we can say, hey, we need more pods. Can you give me more pods? And it may create a purchase order and send out to Dell, so you get another computer delivered on a forklift the next day, and you stick it in and you add it to your cluster. And that's auto-scaling, a very manual process of auto-scaling. But yeah, I think it's very possible today with Container Engine. But again, I'm not recommending you choose Container Engine, but it is one option for that today. For AWS and others, a lot of people run Kubernetes on AWS. It's probably possible to get up to their autoscaler as well. But again, you may be relying on the cloud provider to do the scaling for you, as opposed to having Kubernetes request the autoscaling, which is a bit different.
Cool. Thank you, Mandy.
Thank you very much. Cheers.
So